Okay, ostensibly this thing is live. I don't know. And I don't know how well this is going to work. My connection has been kind of screwy today. So I'm going to wing it. And because of that, I'm not going to go check YouTube to see if this is actually working. I'm just going to have to take it on faith for a moment. Tommy's latest video, he used a quote from, what's his name? Hang on a minute. It's from Stephen Stanley. And the quote comes from page 39 of his book, Macroevolution Pattern and Process. It just so happens I own that book. One of the things I find annoying is the way that a number of creationists frequently use quotes. There are actually lists of various creationist quotes online, and I think they go to some of these lists, they borrow the quotes that the quote that they need for whatever occasion, and they don't bother to look up the quotes, where they come from, what they mean. And this is, they also don't bother to find out whether that quote represents current thinking. You can find a quote from just about anyone in a field to say anything. If you want to be if you want to think the Crusades are just a wonderful, fantastic thing that Europe did, I'm sure you can find a historian that thinks that it's just a wonderful thing that Europe did, but that doesn't necessarily represent, the standard thinking on the subject. And as I said, the other thing is this the current thinking on the subject? So this book, Macroevolution Pattern and Process by Stephen M. Stanley, was published in 1979. It's been around for a while. And let me just give you a little bit talk about the contents. It's called The Fabric of Evolution, is part 1, and the sections are introduction, alternate shapes for the tree of life, the modern synthesis, divergent speciation, the status of quantum speciation in modern biology, the status of quantum speciation in paleontology. Then it goes to the next section, which is called Diverse Lines of Evidence, and that's page 39. Now, what I want to do is I want to read a little bit from the status of quantum speciation in modern biology, and then I'm going to go to page 39 to give you an idea of what's really going on here. So this is page 22, Divergent Speciation. The fact that the fossil record seemed often to document sudden origins of higher taxa troubled Darwin, but was largely ignored by the architects of the modern synthesis, few of whom were paleontologists. Much of the momentum of neo-Darwinism in the early 1900s and of the modern synthesis that followed came from the apparent removal of two impediments that had greatly troubled Darwin and his supporters late in the last century. One development was the general recognition of particulate inheritance, which led to the growth of modern genetics. This recognition eliminated the anti-Darwinian argument that sexual reproduction would automatically blend into oblivion the germplasm underlying a useful new adaptation. Darwin's second major obstacle had been related to the scope of geologic time. Assuming the Earth to be cooling from its time of origin, Lord Kelvin and other physicists calculated that the planet's present temperature permitted its age to be no greater than perhaps 20 to 40 million years. In proposing that natural selection could not form new species, de Vries, 1905, cited Kelvin's calculations. He concluded that speciation must instead occur instantaneously by macro mutation. As noted in Chapter 1, however, the discovery of radioactive heating soon showed the Earth to be much older than the physicists had estimated. The vast expanse of geologic time that Lyellian geologists and followers of Darwin had envisioned was no longer threatened. Buoyed by this development and the rise of genetics, gradualistic Darwinism entered a renaissance. In the chapters that follow, it will be shown that the temporal strictures that had frustrated early Darwinists have by no means been fully removed. As already noted, careful study of rates of evolution and the modern scale of geologic time indicate that the phyletic transformance is painfully sluggish. This conclusion implies that the resurgence of gradualistic thinking after the turn of the century represented an overly optimistic reaction. The age of mammals, the Cenozoic era, is now considered to have lasted about 65 million years. The entire Phanerozoic, extending from the Cambrian, when metazoans first appear in abundance, to the present spans about 570 million years. Such stretches of time seem long until compared to the intervals within which many large-scale taxonomic transitions seem to have taken place. For example, discrete new orders of mammals have arisen at intervals of less than 10 million years. It was this kind of observation that led Simpson in 1944 to postulate quantum evolution. He suggested that this mode of evolution accounted for the origins of most higher taxa by the rapid crossing of adaptive thresholds. The population or taxon making the transition was seen as passing from one adaptive zone or set of related ecologic niches to another by way of an unstable, inadaptive phase of evolution. In 1944, Simpson suggested that most radical types of quantum evolution probably began by random fixation of inadaptive mutations in small, isolated populations. That was a quote from page 211 in his book. This disequilibrium phase, he suggested, was followed by a phase in which natural selection carried the group into a new adaptive zone. What seems clearly to have been described as a form of geographic speciation. Simpson also expressed the idea that a quantum evolution, quote, may be involved in either speciation or phyletic evolution and, ellipses in here, certain patterns within those modes intergrade with quantum evolution, unquote. This is page 206. Thus, he did not restrict quantum evolution to speciation. In his sequel to the 1944 book, Simpson, in 1953, abandoned the notion that speciation is a primary state of quantum evolution. He did remark that species, insert ellipses, often rise in this way by quantum evolution. Page 389. That's kind of a summary, by the way, of what's on page 389. On the other hand, he focused upon phyletic evolution as the source of major adaptive breakthroughs, viewing quantum evolution, in effect, as greatly accelerated phyletic evolution. In discussing the origin of higher taxa occupying distinct adaptive zones, Simpson stated that it is, quote, it is normally phylogenetic, bracket, phyletic as defined in the present book, close bracket, progression rather than speciation that leads into the new zone, unquote, page 350. He then added that, quote, dichotomy or multiple speciation may also occur, but it is not the essential feature of the pattern, unquote, from page 354. In a paper entitled Change of Genetic Environment and Evolution, unquote, Meyer, 1954, established the modern punctuational view with a number of ideas that he later elaborated on in larger works. This is Meyer's works from 1963 and 1970. His primary conclusion was that the origin of species from small, locally isolated populations of pre-existing species is often associated with rapid evolutionary divergence. He extrapolated this idea to paleontology, pointing out that this conclusion may account for many evolutionary gaps in the fossil record. Quote, rapidly evolving, peripherally isolated populations may be the place of origin of many evolutionary novelties. Their isolation and relatively small size may explain phenomena of rapid evolution and lack of documentation in the fossil record, hitherto puzzling to the paleontologists. Unquote. This is from Meyer, 1954, page 179. Meyer opposed the previously cited idea of Sewall-Wright that large populations deployed as partly isolated subpopulations should evolve rapidly. Instead, he suggested that gene flow among populations of a species tends to prevent local populations from adjusting by natural selection to local conditions. Basically, Meyer's idea is as follows. A species is typically deployed as an array of subpopulations that are partly isolated by geographic barriers. Each subpopulation must face a unique set of environmental conditions, but, sorry about that, got distracted. Where was I? Basically, each subpopulation must face a unique set of environmental conditions, but because of some gene flow among populations, local selection pressures will tend to cancel out. It will be very unlikely that the entire species will evolve rapidly in any particular direction. In support of these ideas, Meyer cited studies by Dice and Blossom in 1937 and Hooper, 1941, of small mammals living on lava flows in the western United States. Endemic blackish races of these creatures have developed only on lava flows surrounded by inhospitable sandy desert. Where light-colored rocks are in contact with the lava flows, gene flow with light-colored populations inhabiting the rocks prevents localized blackish races from appearing on the lava flows. In recent years, the notion that gene flow plays a primary role in stabilizing species has fallen into disfavor. Eldridge and Gould, 1972. The reason is that gene flow has been judged to be ineffective. Spread of new genetic material throughout a large species appear to be quite slow. Ehrlich and Raven, 1969, Meyer, 1970, page 300. In the next chapter, however, it will be argued that gene flow may indeed be sufficient to stabilize many species, even though spread of useful mutations may be sluggish. Meyer has placed special emphasis on another condition, 1954, 1963, 1970, 1975, that he believes confers stability on established species, quote, the unity of the genotype, unquote. Obviously, any configuration of genetic material within an established species is adaptively successful. The species exists. Organisms are exceedingly complex entities, and most changes in a genotype produced by random mutations of genes or chromosomes are likely to be deleterious. Given these conditions, Meyer has argued that major changes are not likely to be brought about by piecemeal restructuring of the genotype through the periodic fixation of mutations and new gene combinations. Only sudden restructuring is likely. The adaptive peak concept of Wright, 1932, is instructive here. Wright has viewed species as entities that occupy peaks in an adaptive landscape. There's a figure here. Peaks represent genotypes associated with suites of morphologic characters that have high fitness. The genotypes that underlie valley morphologies, on the other hand, are unsuccessful. In essence, Meyer's argument, like that of Simpson in 1944, is that passage from peak to peak is perilous. It is accomplished only by a rapid genetic revolution occurring within a small, localized population. This isolated population is likely to be occupying an atypical habitat that will impose strong uniform selection pressures upon individuals of the small population. Meyer sees chromosomal restructuring as a common feature of speciation. Heterozygous chromosomal combinations are usually deleterious, so that there is a premium on rapid passage through the heterozygous bottleneck. In part, the rapid divergence may also stem from the fact that the population is a non-representative sample of the gene pool of the parent species. The idea that a biased genetic sample may contribute to divergent speciation is known as the founder principle. Meyer, 1942. The view that evolution can proceed most rapidly in small populations had been championed earlier by Wright in 1940. Who showed that natural selection can operate most efficiently in small populations, and here also genetic drift, or chance change in genetic composition, is more likely to have significant effects. This conclusion might seem to contradict the other idea of Wright that was noted earlier, that evolution is likely to occur rapidly in certain large populations. From the seemingly paradoxical pairing of conclusions emerged the idea that rapid evolution within small subpopulations could accrue to the benefit of a full-fledged species. This belief, which was introduced earlier in the chapter, is still held by Wright. Quote, the situation is much the most favorable for evolution where there can be selection among interaction systems. This can occur within widely ranging species divided into small populations, sufficiently isolated to prevent wide stochastic deviations in numerous loci, but not so isolated as to prevent excess diffusions from those centers that happen to have acquired the most adaptive interaction systems. This is from Wright, 1977, page 471, unquote. Meyer, in contrast, is focused upon isolation as the key to rapid evolution. Clearly, successful speciation is a rare event in the history of a lineage. To take the simplest case, if constant diversity is maintained, an average lineage will bud off only one descendant species before being terminated. Many temporary isolates become reunited with parent populations before diverging into new, reproductively isolated species. Also, Meyer has estimated something like 99% of permanently isolated small populations with the potential to form new species may go extinct without doing so. In effect, these populations fail to cross the adaptive valley. It is also important to appreciate that Meyer's scheme makes no claim that all species arise in association with significant change. Some new species are quite similar to their parent species. Nearly identical species that are newly recognized, that is, were formerly not recognized as being distinct from one another, are called sibling species. Thus, Meyer's argument is that some fraction of speciation events produce rapid morphological divergence and that these account for more net evolutionary change in the history of life. In effect, Meyer focused quantum evolution at the level of the species, and Grant, 1963, who has also contributed much to the study of this phenomenon, coined the useful phrase quantum speciation. The nature of quantum speciation is not yet well understood. Only Meyer's original analysis has been outlined in the preceding paragraphs. Additional views on the subject will be reviewed in Chapter 6 after the importance of the phenomenon has been assessed. Another point that deserves clarification relates to the timing of rapid divergence that is alleged to be associated with some speciation events. Does most evolutionary change associated with quantum speciation occur before or after reproductive isolation has been completed? The question is potentially difficult to answer because if reproductive isolation is of a recent population from the parent species has not yet been achieved, it is not possible to predict when it will be. Similarly, once reproductive isolation has been achieved, its timing cannot be reconstructed from geologic evidence. In fact, there will often be no brief moment at which reproductive isolation can be said to have been achieved. Some distinct species can hybridize to a degree, although hybrids may be selected against, leading to further divergence of the species and development of sterility barriers to those interbreeding. Because of these sorts of problems, consideration of the temporal relationships between rapid divergence and reproductive isolation will be deferred to Chapter 6. For the present, we can define quantum speciation simply as speciation in which most evolution is concentrated within an initial interval of time that is very brief with respect to the total longevity of the new lineage that is produced. Implicit in this concept is the idea that during rapid early phase of evolution, the seminal population has not yet expanded from its small initial population size. Now, I could go on, but I'm not going to. I ended here at page 26. The reason I did that is I wanted to just, lay the groundwork for what, what he's talking about here. And let's go to page 39. So what Stanley is largely talking about here is quantum evolution, something that I think we might think of today as a punctuated equilibrium, or punctuated equilibrium being a form of quantum speciation. Hang on just a sec. I needed to drink something. Now what I'm going to do, I'm almost done, as I'm going to read from page 39. Page 39 is it's not even the introduction. It's the front statement from page 3 called Diverse Lines of Evidence. Okay. Some distinctive living species clearly originated in the very recent past during brief instants of geologic time. Thus, quantum speciation is a real phenomenon. Chapters 4 through 6 provide evidence for the great importance of quantum speciation in macroevolution, for the validity of the punctuational model. Less conclusive evidence is as follows. 1. Very weak gene flow among populations of a species, a common phenomenon, argues against gradualism because without efficient gene flow, phyletic evolution is stymied. 2. Many levels of spatial heterogeneity normally characterize populations in nature, and at some level, the conflict between gene flow between subpopulations and selective pressure within subpopulations should oppose evolutionary divergence of large segments of the gene pool. Only small populations are likely to diverge rapidly. 3. Geographic clines, which seem to preserve in modern space changes that occur at evolutionary time, can be viewed as supporting the punctuational model, because continuous clines that record gradual evolution within large populations represent gentle morphologic trends, while step clines seem to record rapid divergence of small populations. 4. Net morphologic changes among major phylogenetic pathways generally represent such minuscule mean selection coefficients that non-episodic modes of transition are highly unlikely. Quantum speciation or stepwise evolution within lineages is implied. 5. The known fossil record fails to document a single example of phyletic evolution accomplishing a major morphological transition, and hence offers no evidence that the gradualistic model can be valid. Evaluations of overall genetic distance, which ignore the fact that large evolutionary steps result from a very small number of regulatory genetic changes, have little bearing on the distribution of morphologic changes within phylogeny. Okay, so the part that Tommy quote mined is 5, where he says the known fossil record fails to document a single example of phyletic evolution accomplishing a major morphologic transition, and hence offers no evidence that the gradualistic model can be valid. Okay, but remember what was said in the beginning. He says, thus, quantum speciation is a real phenomenon. Chapters 4 through 6 provide evidence for the great importance of quantum speciation in macroevolution, for the validity of the punctuational model. Less conclusive evidence is as follows. And then he lists 1 through 5. So he's going to explain the evidence for quantum speciation in chapters 4 through 6. But before he does that, he just honestly lays out that there are these 5 objections. Now, are these 5 objections going to be addressed? Well, we'd have to read on to find out. How much do you want to bet Tommy has not read on to find out? Also, remember, this book is from 1979. So what I'm going to do is I'm going to read out all of page 39 again, and then I'm just going to close this because basically this is all I wanted to do. I wanted to put Tommy's quote in context, since I'm pretty sure he has no clue what the context is. So here we go. Chapter 3, Diverse Lines of Evidence. Some distinctive living species clearly originated in the very recent past during brief instance of geologic time. Thus, quantum speciation is a real phenomenon. Chapters 4 through 6 provide evidence for the great importance of quantum speciation in macroevolution, for the validity of the punctuational model. Less conclusive evidence is as follows. 1. Very weak gene flow among populations of a species, a common phenomenon, argues against gradualism because without efficient gene flow, phyletic evolution is stymied. 2. Many levels of spatial heterogeneity normally characterize populations in nature, and at some level, the conflict between gene flow between subpopulations and selection pressure within subpopulations should oppose evolutionary divergence of large segments of the gene pool. Only small populations are likely to diverge rapidly. 3. Geographic clines, which seem to preserve in modern space changes that occurred in evolutionary time, can be viewed as supporting the punctuational model because continuous clines that record gradual evolution within large populations represent gentle morphologic trends, while stepped clines seem to record rapid divergence of small populations. 4. Net morphologic changes among greater phylogenetic pathways generally represent such minuscule mean selection coefficients that non-episodic modes of transition are highly unlikely. Quantum speciation or stepwise evolution within lineages is implied. 5. The known fossil record fails to document a single example of phyletic evolution accomplishing a major morphologic transition, and hence offers no evidence that the gradualistic model can be valid. Evaluations of overall genetic distance, which ignore the fact that large evolutionary steps result from a very small number of regulatory genetic changes, have little bearing on the distribution of morphologic changes within phylogeny. So that's about it. And thank you if anyone bothers to listen to this. I'm going to close the live part, and goodbye. Hang on just a second. As soon as I